Welcome to the Mac 2313 Calculus 2 Optional Exam Review. My name is Danny Joseph. I'll be your host today, and we're going to go over a few problems that was in our optional exam that we're going to go ahead and review and find out how we would get to the solution that we went ahead and submitted while we took the optional exam. So bear with me. We're going to go ahead and knock out a few problems, and hopefully you guys leave after today's video knowing a little bit more about Calculus 2. All right, so we'll be working on problem number 2. Find the volume of the solid generated by revolving the region bounded by the graphs of the equation y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 along the y-axis. So we have a few things to consider when we're looking at a problem like this, and I'm going to underline those things that we want to consider. So of course the equation itself, the function, y equals x squared plus 1, we want to keep in mind x equals 0 and x equals 1. All right, and I'll kind of explain why that matters in a little bit. But of course, what I always would recommend is drawing the graph. Of course, since I'm using a whiteboard, I don't recommend my own drawing, but I do recommend you guys maybe crunching that into a graphing calculator or just graphing it yourself just to see what the actual equation comes out to be on the graph itself. But since we're going to go ahead and just kind of deconstruct a little bit of what's going on here, what we're going to do is apply a formula that would convert this function into a integral where we can find the volume itself. So what that would look like here would be the following. Knowing what we know, we have the integral of a and b, right, with pi inside times the function squared dx. Okay, so knowing what we know there, we're going to go ahead and start plugging in some of the things that we know from the problem that it gave us, right? So we know that the function is going to be x squared plus 1. And now when we look at the bounds, that's where I underline the x's. That's what we're going to consider as the bounds when we go to solve this integral that'll give us the volume. So we'll remember that this is equal to the volume. So let's go ahead and plug in some of those numbers there and find out what we get. So the volume is now equal to 0 and 1. And then of course we have the pi, which doesn't change, but the function, which is x squared plus 1 squared dx. All right, beautiful. So now we have a functioning integral that we can go ahead and try to break down that will then lead us to the volume in which we're looking for. So with that being said, we're going to go ahead and make our lives a little bit easier. We have our pi that we can bring outside the integral to make things just look a little bit prettier. So what I'm going to go ahead and do is just kind of use our blue marker to show what we're going to be planning on doing. And then, of course, what we could also do is solve the math of what x squared plus 1 squared would be. So one thing that a lot of people will go ahead and do is say, okay, well, x squared plus 1 squared, well, that's just going to give you x to the 4th plus 1, right? Wrong, actually. So you don't want to think in that manner, because what we're actually doing, and again, I'll use this blue arrow here, what we'll actually be doing is the following. So it's actually going to be x squared plus 1 times x squared plus 1. That's going to give us a completely different answer when we're considering these things, because we're going to be foiling now. So we're going to be doing x squared times the x squared, and then x squared times the 1, and then the 1 times the x squared, and then the 1 times the 1. So let's keep in mind, when we do that, we're going to do x squared times the x squared, which is going to be x to the 4th, right? Then we're going to be doing x squared times the 1, which as well is x squared. Then we're going to be doing 1 times the x squared, which is another x squared. And then we're going to be doing the 1 times the 1, which is just 1. course, this is still within the bounds of the integral. And then now we have our pi outside. And this is all going to equal our volume. So, with that being said, we're almost done. We have a few things that we would want to do, but we need to make sure this we do it correctly so we don't lose the flow of what we're doing here. So, what else will we do from here? Well, I would recommend at this point breaking down each individual part of the integral and simplifying this as you go along. Well, one thing we can do before even doing so, what I'll make our lives a little bit easier, is doing the following. So, plus, but instead of having the x squared and the x squared, we'll just say 2x squared. All right. So now, let's free up some space on our board. Subtract that from the board. Okay. So now we have exactly what we left off with, which is the volume equals pi of the integral from 0 to 1, meaning the bounds, of x to the fourth plus 2x squared plus 1 dx. So, like I recommended before, what we're going to go ahead and do is simply find the integral of each denomination there. So, what I'll go ahead and do is bring the first term here, and that's x to the fourth, down here, and we're going to find what the integral of x to the fourth would be. So, the integral of x to the fourth, we remember how we would find that is we would actually do a plus 1 to the exponent and then put it over a denominator of the exponent plus 1. So what that means is essentially you go from x to the fourth to x to the fifth plus 5. Oh, I'm sorry, x to the fifth over 5. I do apologize. Misspoke there. And then, of course, the bounds being 1 and 0. And then we'll do the same thing here. We'll do, for the 2x squared, we're going to actually have 2x to the third over 3. And then the 1, in this case, actually just becomes x. And then, of course, the bounds. Okay. So now, at this point, we're going to go ahead and simplify this even further. So, what we're going to go ahead and do is substitute the x value for our bounds. Well, we know right off the bat, whenever we're using 0 and we're dividing anything by 0, it is 0. So we won't have to worry about the 0 bound. But let's think about the 1 bound. Well, 1 to the 5th power is still 1. So that's going to give us 1 over 5. Which we'll write. Actually, let me move that up so you guys can see that. 1 over 5. Alright, and that's what we got when we plugged in the 1 for the x. Alright, so the next value we're going to have is we have the 2x to the third over 3. Well, again, what we're going to want to do is plug in the 1. 1's going to be 1 to the third power is still 1 times 2 is 2. So that's going to give us 2 over 3. And then, of course, we won't have to worry about the 0. And we have x equaling 1. So we'll add these together to give us what we want. Now, let's not forget that we still have a pi outside of our integral. So technically, these are still going to be multiplied by pi. But we have a few different fractions that we can't just add together with how they are now and how they're presented. So what we're going to want to do is make sure that we find a common denominator, and then we can add these fractions together. So with that being said, let's go ahead and focus on what we have so far. So we have 1 over 5 plus 2 over 3 plus 1. Well, the common denominator of 5 and 3 is 15. So what do we need to do to get to 15 for each of these fractions? Well, let's focus on that over here on this side. And for 1 over 5, we're going to times the denominator by 3 to get 15. But whatever we do on the bottom, we got to do on the top. So what I'll do, just so we know exactly what's going on. Times by 3 times by 3. So we're going to have pi times 3 over 15 plus, and then for here, to get 15, we're going to actually times by 5. Times by 5. Okay, so instead, we're actually now going to have, instead of 2 over 3, we're going to have 10, because 2 times 5 is 10, and over 15. And then this last little bit, you're wondering, well, we have a 1. Well, 15 over 15 actually gives us 1. So we know that the 1 value is actually going to be 15 over 15. And then again, all that is going to be multiplied by pi. Well, let's do some simple addition. Well, 3 plus 10 is 13. 13 plus 15 is 28. So that's all going to be over the common denominator of 15. So that's now going to give us the new value of 28 over 15 pi. Because remember, we had the pi outside. And that will give us our volume for this function. All right, so we have problem number 4. Now, problem number 4 says, solve the integral of, we can consider this dx, or 1 over the square root of 4x squared plus 1. So, how would we kind of go about this? Well, this one's going to be a little bit different because right now, in its current state, in my opinion, this looks pretty ugly. So, let's kind of simplify it a little bit. We're going to want to take a look at that denominator and do a couple things with it. So, first thing that I would do is go ahead and I would simplify this denominator here, because the denominator with that square root and everything, I'm not really liking that. But the nice thing is, finding the square root of this, it's going to be very simple. So we can rewrite this after finding the square root to be, and I'll just draw my handy dandy arrow. All right. So it's going to be the integral of 1 over 2x plus 1. Now, let's think about that real quick, what we did there. Now, of course, the square root, if we were to square this, it would change that to 4, and this to an x squared. Well, the square root of 1 is 1. So that's how we got the 2x plus 1, just in case if you were a little lost in how we got there. And let's not forget the dx. Now that we have this integral now to work with, it's a lot simpler in what we're going to plan on doing. Now, from here, we can just do a simple u substitution. So with that u substitution, we're going to want to substitute that ugly part that we have there. So that's going to be the 2x plus 1. Well, du, if we're doing the u substitution, will then become 2 dx. Or we can look at it like it will be 1/2 du dx. These are literally the same values. So just in case you were wondering how do you get that, what I went ahead and did is just divide the 2 over on the other side to give us 1 over 2 du dx. That's going to come in handy in just a moment, and you'll see how we're going to implement that into the current integral. So now that we know what we have for our u and du values, we're going to go ahead and just plug that back into the integral. So what that's going to give us now is the new integral of the following. 1 over, and then now this is going to be a 1 over u, and then the dx we know is 1 over 2 du. So that's going to be 1 over 2 du. So what we're going to go ahead and do now at this time, we have 1 over u times 1 over 2 du. Well, we're going to make our lives easier because that's what we like to do. We want to try to solve these integrals as easy as possible. So again, now that we have the 1 over 2, I'm just going to get rid of that. I'm going to put that in outside the integral because we're allowed to do so. And that's going to give us the new integral of the following. 1 over 2 the integral of 1 over u du. Now, right off the bat, if you guys already know some of your formulas, you should already recognize what that 1 over u is going to provide us. 1 over u, the integral of 1 over u, or 1 over x, is going to give us the natural log of that variable. And then, of course, we have the 1 over 2, so we have to remember to multiply that out. So what that's going to actually leave us is the following. And I'll put that down here. So it's going to actually give us 1 over 2 times the natural log of u, and of course we put it in those brackets there, plus c. Right, so now what we're going to want to make sure that we do is we substitute the u that we have with our original value, because again, what we want to remember is that we started with an x. So when we get our value, we want to end with an x. Well, we already know what the u value is. It's 2x plus 1. So we're just going to go ahead and substitute, and I'll draw an arrow here just so you guys can understand my logic. We want to substitute the u for what the u value actually represents. So that's going to leave us with 1 over 2 of the natural log of 2x plus 1 plus a constant. And that, ladies and gentlemen, will be your final answer. We have problem number 5, where it's asking us to solve the integral of 1 over x cubed plus 4x dx. Ugh, man, does this look ugly. But thankfully, there's an easy way to solve it. Now, when I say easy is kind of relative, so bear with me. We're going to kind of explain some of the process, the thought process, to go ahead and solving a problem like this. So when I look at this, I look at a few things. And when I'm looking at the bottom is a little bit more complicated. And if we were to try to do the u substitution, it's not necessarily going to make things that much easier. But something we could consider is maybe a partial fractions. But right now, in its current form, it just wouldn't work out. But there's a way we can simplify it so that it could work out. So let's go ahead and convert this. I like to draw these transition arrows so you know where we're going, because there's going to be a lot of things on the board and I don't want you to get lost. So we're going to go ahead and do the integral of, now let's look at this here. Look at these two factors here. Well, the common factor between the both of these is actually x. And what's nice about that is if we remove the x outside of these two common factors, we actually get something that we can then use a partial fractions for. What that something is 1 over x times x squared now plus 4. And that looks very recognizable, right? Well, that's exactly the key of what we're trying to find out here. So keep that in mind when we're looking at that. But when we're looking at partial fractions, we're going to need to break this up now. So when we're breaking it up into a partial fractions related equation, we're going to then consider each little factor of what we just created now. So we have the x and then the x squared plus 4. Now for the x, it's very simple. It's very straightforward. So then we're going to have a, try to write that a little bit better. I don't know why the market's not picking that up a little bit. But a over x plus, now we have the second part. This is where it's going to be a little bit interesting. B x plus c over x squared plus 4. All right. Now, we can go in a little bit further detail why you would want to do the bx plus c, because of course the term, the exponent term, is higher in this specific term than it would be with the x. That's why we only have to keep one letter a. But since we're dealing with an x squared, we have to make sure that we keep things congruent. So you'll see how that plays out in just a moment. Now that we have what our partial fractions would be, we have to keep in mind that this is all equal to each other. So technically what I'll go ahead and do, I'll remove this little arrow here. actually equal these to each other. Well, what you want to keep in mind is because they're equal to each other, we can simplify this a little bit further. Now, keep in mind what I would do to simplify this a little bit further is use what we have as a denominator and clear that up. But how we do that is we have to multiply the denominator by the other side. So when we do that, we know that multiplying the x times x squared plus 4 against the x, that's actually just going to cancel out the x and leave us the x squared plus 4. So I'll say, right? And then here, it will do the opposite. So it's actually going to cancel out the x squared plus 4, but leave us the x. So, in turn, what we're going to have now is the following. We're going to have 1 equals, let me remove that. So we're going to have 1 equals a times x squared plus 4. And then we're going to do plus x times bx plus c. All right, so that's going to be our new equation for the time being until we can get back to the integral side of things. So we want to solve for a, b, and c. Well, how are we going to go ahead and do that? Well, I want to plug in a term for x that will help basically simplify the equation so we can just focus on a. So what we will do is we'll start out with 0. So we'll say x equals 0. When we do x equals 0, what's nice is anything times 0 is 0. So we know that timesing this whole portion by 0 is going to give us 0. Then over here, we're going to also do 0 for the x value, but that's going to be 0 squared, which is still 0, but at least we have the 4. So what that's now going to change things into is going to change the equation to say 1 equals a times 4, because we know 0 plus 4 is 4, and then this cancels out, so we won't even have to worry about the rest of that. So we know that all of that cancels out. So from there, to simplify so we can get the value of a, we know that that is going to translate to dividing 4 on each side, giving us a equals 1 over 4. So we solved one of the variables there. So I'm just going to stash that over here to say that a equals 1 over 4. Beautiful. So now we want to find what b and c and their values equal out to. So to find that, we're going to need a different variable that's going to help us out a little bit because we want to get rid of the a here. So that's going to be a little bit more challenging. So let's keep in mind, we're going to go ahead and rewrite this here to what we originally had. So we had a x squared plus 4 plus x bx plus c. All right. So now at this point, instead of using 0, we're going to give it the value of, let's just say 2. So with the value of 2, we're going to go ahead and plug that back in. So that's going to give us 1 equals 2 to the 2 squared is 4. 4 plus 4 is 8. So that's going to give us a times 8. Plus, now we're going to have a 2 out here. So we're going to have 2 times bx plus c. Now, with that being said, we'll go ahead and say here that the bx is going to be b2 plus C. So what in turn is that going to give us? Well, we're going to multiply the 2 and the 2 here. So now we can rewrite that as 1 equals 8 times 8 plus 4b plus 2c. Awesome. Now, you're probably wondering, Danny, we didn't get rid of the a. Well, technically, we already know what the a value represents. It's 1 over 4. So we can plug the a for 1 over 4, meaning that we technically now would have 8 over 4. And 8 over 4 we know equals 2. So we can then say that this new value will equal 2 plus 4b plus 2c. Well, let's make our lives a little bit simpler. We know, let's get rid of the 2. So we're going to minus the 2 from each side. So minus the 2. This cancels out. Minus the 2. We are left now with a 1, a negative 1. So now we're going to draw a transition arrow to say that negative 1 is equal to 4b plus 2c. Now, what we can do now is consider the following. If we know that we can divide the 4 on both sides, that's going to mean that b is equal to negative 1/4. Because c would then have to equal 0. Because we know that if b equals negative 1/4, then whatever c has to be can't influence the value of what we already have b to equal to. So we have to say that c is equal to 0. So that's how we find out all 3 of those variables. So now that we have those variables, we're not done. We got to then plug this back in to our integral. We have our values here on this side. And what I like to do is consider separating those integrals so that we can make sure that everything is flowing and easily readable within our solution. So one thing we're going to have the a over x like we stated before. So we're going to have the integral of a over x. We know a equals 1 over 4. So that's 1 over 4 over x. And then we put the dx. Plus the bx plus c over x squared plus 4. Well, we know now that it's going to be plus the integral of bx plus c, which is the same as saying negative 1/4 plus 0 over x squared plus 4 dx. Now, I'm just going to focus on one side first, and then we're going to get to the other. So with the first side here, we can bring that in and simplify it. What I like to do is make my integrals look as easy as possible. So what we're going to do here is actually bring the 1/4 out in front of the integral. So what that's going to leave us now is a new integral of 1/4 integral of 1 over x dx. And just like what we had with our previous problem, we know that the integral of 1 over the variable is a natural log of that variable. So we can then hypothesize and say that this is now going to equal 1 over 4 times the natural log of x. And then, of course, we have a constant, but we have a little bit more math to do. So we're just going to keep it at that for now. Now for here, this is going to be a little bit more complex. We want to start by doing the same thing we did over here by bringing the 1/4 out. We're going to bring both the 1/4 and the 0 out. So what that's going to leave us is now, and I'll separate this by drawing a line so we don't get confused. We're going to now say negative 1/4 over 1 over x squared plus 4 dx. Now we're not done. Obviously we don't have like a quick little, oh, this converts to what? But we know from our last problem that we can do a u substitution. So if we do a u substitution here, we can say u equals x squared plus 4. And so that means the du would be equal to 2x dx. So we're going to go ahead and plug that back in. So we're going to do negative 1/4 integral of 1 over u times 1/2 du. Now that we have that, we can then simplify it even further by bringing out the 1 over 2 to our already existing 1 over 8 to make it negative 1 over 8. And then we have 1 over u du. So, of course, just like what we had before, that's just going to then become negative 1 over 8 times the natural log of u, which then converts to what the value of u is, which we'll say in this case is x squared plus 4. Let's say x squared plus 4 with our brackets there. And then now we can say our final answer is 1 over 4 ln of x plus, or I'm sorry, minus 1 over 8 ln, So now let's go ahead and rewrite our solution here now that we have every variable. So we're going to have 1 over 4 times the ln, get my markers like giving out on me, 1 over 4 times the ln natural log of x minus 1 over 8 natural log of x squared plus 4, and then plus c. And that will be our new answer. So, guys, we have problem number 7. Problem number 7 is a little bit different from the structures of our other problems. It's actually more of a true or false. It's a true or false based off if the function given is converging or if it's not converging. So if the series that the professor has provided is converging, we'll say true. If it's not converging, if it's diverging or inconclusive, we'll hit false. So we'll start with A. A says cosine of the fraction n pi over 2. Is this converging? So essentially what you would want to do is run a test to test if this series would be converging. I did so on the side because, of course, since we have a lot of problems, I don't want to hold you up. But we find out that the limit is actually infinite. So that means that this one is false because it actually is diverging with a limit of infinity. Moving on to B, we want to go ahead and check the same thing. What I went ahead and did is I made sure we checked and I'll put this on the side here. We went ahead and ran the tests where we want to go ahead and put our series against this formula here. When we do, we find out again that the limit is infinite, and so that it is diverging, making this false as well. Now, when we're looking at the natural log, once we check the natural log of 1 plus 2 over n, we wanted to run a integral test to find out for this one here. So this one for C would be more of an integral test that we'll be running. But again, we do find out that it is indeed diverging because the limit hits infinity. So We'll go ahead and hit false. Then for D, we have cosine of 1 over 2 to the nth power. For this one, I ran a divergence test, found out that the limit is equal to 1, but because the limit is equal to 1 in a divergence test, that also means that it is diverging, so that is false as well. For E, we are looking at E, and we're finding the summation series from with n equaling 1 and the top being infinite of 1 over 2 to the nth power. And for this one I also found out, so ironically, from the geometric test that I ran, that this one is actually indeed converging. So this one is true, and then it is actually converging into a lesser known value, and we'll have to worry about that one there. So for F, we have, again, the summation with n equaling 1 of cosine n times pi. For that one, we ran the divergence test, and again, we found out the limit was actually infinite. So this indeed is false because it is diverging. Then we go to G. G with the summation with n equaling 1 of 1 over n times n plus 1 equaling 1 over 2. We found out that this one is actually converging using the telescoping series test. So we found out since this one is converging, it is actually true. And then with the last test, it's the summation with n equaling 0 of x to the nth power equaling 1 over 1 minus x. We find out that this series is actually diverging, making it false when we use the root test. So, as we can see here, of the problems given from A to H, there is only 2 problems, E and G, that are actually converging, and the rest are actually diverging. Problem number 8. Consider the power series of negative 1 to the n power times x over 3 to the n power, using the appropriate test to find the radius of convergence and the interval of convergence. So I have I have a ratio test standard on the left here that just states that if L, the limit, is less than 1, it converges. If it's greater than 1, it diverges, and if it's equal to 1, it's inconclusive. So we're going to need that later down the road, and you'll kind of see why we need that. So let's take into consideration a few things. Based off that, we know that the limit is equal to the x over 3. All right, so if the limit is equal to the x within the brackets there over 3, what we can consider now is the ratio test that we have. Now, if that is to be true, then we know whatever x over 3, I'm thinking that's going to be less than 1. So we put the less than 1, and based off that, if we're just thinking right off the top, if I put a 1 value for x, 1 over 3 is going to be less than 1. So that's already having me think that this is going to be converging. So with that being said, though, we'll say the limit is less than 1. And how we can go ahead and simplify this so that we have the x value by itself, we're going to want to times this by 3. But whatever we do on one side, we have to do to the other. So we need to times this by 3, giving us the value of x within the brackets less than 3. So now we know that the radius of the convergence, well, let's say of the convergence is equal to 3, and then the interval of that convergence, because it could be either a negative or a positive, because regardless it's going to give us 3, is going to be 3, and positive 3. Okay, so we have problem number 9 that says prove the series of n plus 2, the factorial over n is convergent. And then it also says that we need to find the Maclaurin series of the function cosine x. So let's start with the first question here. Prove that that series is convergent. So we're going to do a few things. First thing we're going to do is, first thing that we're going to do, and don't mind that I'm using blue when black marker ran out, so we're moving along with things. So we're going to go ahead and knock out this one. We know that a n plus 1 over a n, right? So we're going to equate that to the equation that or the series that they provided to us. So how that's going to go ahead and be translated is we know that it's going to then be, since we have an n plus 2 factorial, we can say that it could be n plus 1 plus 2 factorial over n plus 1 factorial over n plus 2 factorial over n factorial. And we keep it all within these brackets here. And now, as we look at what we would need to do next, we can then simplify some of this to say that, again, we want to make sure we keep these brackets. N plus 3, which is exactly what we had here, factorial over n plus 1 factorial over n plus 2, just like what we had before, over n factorial. All right. Now you're probably wondering, all right, where are we going from this point? Let me add this here. And you're probably wondering, all right, where is this going? Where is this leading on to? Well, we want to keep in mind that we have some factorials. So we could actually simplify a lot of this problem here by doing the following. So again, we have n plus 3 factorial plus, or over n plus 1 over n plus 2 factorial over n factorial 1. So now you want to keep in mind, we're going to want to bring over the bottom factor. And since we have this one here, when we bring this back down, that's going to change things around so that we can then manipulate the equation and simplify what we have. So what that's going to indeed then end up having is the following, which is going to be a n plus 3 n factorial, and then you'll have your n plus 1 factorial and n plus 2 factorial. All right. So, and then from there, we find out that we can go ahead and cancel some factors here. We can go ahead and cancel out the fact that we have the n and the n plus 2, leaving us with just the n plus 3 over n plus 1 factorial. So now, or I'm sorry, we're going to just have the n plus 3 and the n plus 1, which I'll write that here so we're not as confused here. N plus 3 and the n plus 1. All right. So now what I'm going to do, I'm going to simplify a little bit of what we have written down. So n plus 3, n plus 1. We can go ahead and simplify some of that. So now we have n plus 3 over n plus 1. Well, if we transition that to a limit equation, we know that while the limit is approaching infinity, we could say, based off what we have, that instead of n plus 3, we can say 1 plus 3 minus n, and 1 plus 1 over n. Now, ironically enough, we know right off the bat, if n is approaching infinity, that we could say that here, that's the same as saying 1 over infinity, which we know is 0. And over here, it's 3 over infinity, which we also know is 0. Okay, so since we know both of those are 0, they technically will cancel themselves out, and all we will be left with is the 1 over 1. Well, of course, 1 over 1 is equal to 1. And we know if L, the limit, is equal to 1, then the series is inconclusive based off the ratio test. So that actually solves the first part. So the series is not actually convergent, but it is inconclusive. So this next part says find the Maclaurin series of the function cosine x. So what we're going to go ahead and do, we know that we need to apply the Maclaurin formula. Now the Maclaurin formula is going to say, and I won't necessarily say the exact formula, I'm going to incorporate our function in it. It's just basically saying that in the series, we'll start with 1, because we're always going to start with 1. And then it's going to say find the derivative, d over dx, of cosine, because that's our function, right, over 1 factorial. Then the next one's going to say find the second derivative of cosine x over 2 factorial. And of course you have x, let me not forget the x out here, and an x squared. So you can kind of see the pattern that they have, and they just want you to continue to keep adding and adding and adding as the series grows. So how do we incorporate that for ours? Well, we already know that we have our function that we have to find the derivatives. So what that in turn is going to lead to is the following. Once we plug in those values in, you're going to get a 1 plus 0, 1 factorial, x. Then you're going to get plus a negative 1, because we know cosine, and that would the second derivative of cosine is negative 1 over 2 factorial x squared. And then, of course, the next one will be 0, because, again, we go back to the next derivative of cosine, which is 0, and then 3 factorial, x to the third, and so on and so forth. So 4 factorial, x to the fourth, and so on and so forth. So just keep in mind with the cosine factorials that you're going to be swapping in between every even derivative that we do. It's going to go from negative to positive to negative to positive. So what the question is asking us is to do the first 5 non-zero items. So these technically would be 0 items, because anything over 0 is going to be 0 regardless. So we want to think of these, of the non-50 items that they're looking for. So let's rewrite it, only thinking about the first 5 non-zero items. So 1 would be the first one. And then, of course, since we have a negative 1, I'm just going to go ahead and say negative 1 over 2 factorial x squared, just like we said before, but we know the next one's going to be 1 over 4 factorial x to the fourth minus 1 over 6 factorial over 6, and then plus a 1 over 8 factorial x to the 8, giving us the first 5 non-zero items there. And that is the answer to the second question. All right, thank you guys for bearing with me. I hope you guys took away a little bit of some helpful tips when it comes to Calculus 2. But if you did, don't forget to like, comment, and smash that subscribe button if you guys want to stay tuned for more tips, more tricks, and more helpful advice when it comes to Calculus 2. I've been your host, Danny Joseph, and you guys have a great day.